Good evening, everyone. Welcome. Chris Rose told me that I am representing Brown University here, so I'm a little scared by this. My name is Leah Van Wy, and I'm the Dean of the Faculty here at Brown. And so I want, on behalf of Brown, to welcome Professor Nadya Mason. Hello, on the other side of the screen. So I'm going to give a brief introduction, which I hope will embarrass Nadya completely, so that then Chris can embarrass her even more, and then we can all learn something. So I'm super excited to be here, partly because I will be able to learn something. I started reading Nadya's lab page because I was like, okay, I'm going to say something smart about the physics. I can't say anything smart about the physics, so I'm looking forward to learning something today. So Professor Nadya Mason started her time in higher education at Harvard University, completing a bachelor's in physics there before going on to Stanford to complete also a PhD in physics. And so after a short stint back at Harvard for a postdoc, Professor Mason moved to her current home at the University of Illinois at Urbana-Champaign, where she has been since then. And we were having an interesting conversation about the differences between small private universities and large state schools. And so she's been very successful there at UIUC. She's steadily moved up in her career over the last almost 20 years. And she's currently the Rosalyn Yalow Professor of Physics at UIUC. And she's conducted research over this time at the interface of nanotechnology and quantum sciences, and that's what we're going to hear a little bit about today. And her work has brought her scholarly prominence across a number of different areas and merited election into both the National Academy of Sciences and the American Academy of Arts and Sciences. And so beyond the science, which we're going to hear about in just a minute, really importantly for this series and for my view here at Brown, Professor Mason has also been a leader and a mentor and a role model for physicists of all sorts, but particularly for women and minorities moving into this important field. She has directly mentored 32 graduate students and postdocs, and has also served in leadership roles promoting diversity in STEM and in physics more specifically, both on her own campus and nationally. And finally, I wanted to mention Professor Mason's recent appointment as director of the Beckman Institute for Advanced Science and Technology. So this was particularly exciting to me because it's not here, but it's a very Brown sort of place because it is an interdisciplinary institute of long standing that is designed to bring together science at the interface of technology and basic science in areas like bioengineering and molecular science and quantum sciences. And so it is kind of has the same ethos and spirit as a lot of the work that we do here at Brown. And so today, Professor Mason is going to share with us a talk entitled The Disappearing Chip, How Quantum Nano-Electronics Disrupts Our Lives. And so I'm saying welcome on behalf of Brown University, and then Chris is going to give another welcome as well. So welcome, Professor Mason.
Okay, so I'm probably going to need help here. Let's see. Nope, I may not need help. This is great. So everybody has one of these, right? Okay. So Leah basically did that. I never do this, and that's not why we invite people here. Nadya is certainly accomplished and absolutely wonderful professor, well known, and she's kind of just beginning. For me, she's just a baby. She's just got all these kudos and everything. So what I wanted to do was, as I do with this particular talk, is tell you a little bit about the person and why I invited them. Again, because this is kind of a special series. Thinking out loud, we're looking for people who think differently, who look at the world differently, and can really eventually, before and even eventually, make tremendous breakthroughs. So, with that in mind, let's see if we can get to the first one. So here's the essential Nadya. Now, I was going to be really intrusive, because I know a lot of people, and I know a lot of people who are not academics. I know a lot of athletes, okay, of various stripes. So the first thing that I'm going to show you is that Nadya's a gymnast, and I don't mean like oh goodness, here you got a trophy for participation. This is Bella Caroli's group that she was a part of, and I guess you were.
Very young.
Like 10 or 12?
No, 13.
13, 14. Teensy there. So, you know, this is, this is somebody that had their eyes on the Olympics and then said, nah, I'm going to do something, I'm going to, you know, concentrate on other things. So the other thing is, you know, she's a mom, and, you know, that's, for me at least, being a parent is the thing. All this other stuff is just frippery. And, you know, of course she's accomplished. She's on 2 academies so far. And she'll probably get tapped for other things, you know, because that's just the way these things go. You know how that goes, Nadya. She's a role model. For those of you who know what Essence magazine is, it's a black publication, women's publication, and she's one of the Woke 100. And that wasn't, again, they don't just give these away. She really has been a role model and an inspiration for what has to be, I'm sorry, I'd say a generation. It makes you feel older than you are, but a generation of young women.
Okay, you call me young already.
Yeah. All right, so, you know, it balanced out. Okay, you know, she's also an, you know, deep intellectual, you know, and I looked at this and I said deep, but she works on a lot of planar materials, so, you know, she's a deep planar person. And is Jim Vallis here? Yeah, so, yeah, right, so, you know, you guys got, you and Mike, did Mike make it? You know, you got a lot to talk about. Mike, our Nobel laureate, you know, because it's, you know, it's 2D materials. So it's going to be interesting to see what happens there if you, you know, if you continue that and don't get sucked into management, which sometimes happens. The other thing that is, again, interesting is this is just one blivet, but she does a morning show occasionally. And it's, you know, like Good Morning America. This is a local version. I guess it's called The Morning Show. And here, I couldn't figure out exactly what she was doing, but there was a bunch of them. And she kind of explained science to just regular old people. And the poor hosts, they didn't know what they were in for.
I know it. I'm mixing hot and cold food dye to show the mixing of the different, how thermal. See, right?
Couldn't educated us here, because I had no idea. So, this is the one. Now, this is the one that got me. So, you know, if you, no, she's not just leaning there. You know, I can't believe that she just sat in the seat and kind of leaned over to the kind of, she's kind of gyrating it and playing with it and seeing how it operates. And that's the and this is the last slide. That's the primary thing for this particular series. The people that come here to give this talk have to be playful, curious, a little bit crazy, because that's how you make the breakthroughs. So with that, Nadya, welcome, and we're really looking forward to your talk.
Okay, well that was collectively the best intro I've ever had. So kudos to you guys. That was fantastic. And I am thrilled to be here. And thank you for setting up this series, Chris, because I think that it's impactful clearly, and it's been a really wonderful day meeting people from all across the campus. And I'm excited to be following in the footsteps of others who have come before me and given these great colloquia. So thank you again, and thanks to everyone who came today. Okay, so I'm talking about the disappearing chip, how quantum nanoelectronics disrupts our lives. And disruption is kind of a loaded word. It's kind of a scary thing. So at first I was worried, you know, am I overstating the case? Is it really a disruption? But no, I wasn't, because there's nothing more disruptive than, say, an industrial revolution. And it turns out that nanoelectronics is the basis for not just the most recent industrial revolution, the one from the past, 60 years, which has to do with the invention of computers and electronic devices, but of the most current industrial revolution, which has to do with the integration of these electronic devices into our lives. So disruption is not overstating it. Nanoelectronics really are there. And I have to admit that, okay, before seeing this, I actually didn't know that there were 2, 3, and 4 industrial revolutions. But I do think it's really cool that we're in one right now, right? And this is really still going into the electronics age. We're on the verge of really exciting things. And the basis of this is nanoelectronics. Okay, so today I'm going to talk about nanoelectronics, their history, why we can or cannot keep making them smaller, and what that means for future devices and even current societal issues like the supply chain problem. Okay, so I'm going to talk about various aspects of nanoelectronics. It encompasses different things. For example, it encompasses just making existing devices smaller. It encompasses using new types of nanoscale materials, material discovery. Also, just understanding the basic physics of small structures. This matters to me because I'm a physicist. And also, I'll touch a little bit on using behavior beyond conventional electronics, like the quantum properties of these, to make new sorts of devices. Okay, so as you guys probably know, nanoelectronics are everywhere. And I think, if I'd shown this slide a few years ago, people maybe wouldn't even realize it, but with all sorts of, the chips being in the news these days, you know that, we have our electronics, our computers, our phones, but there are also small-scale electronics in our washing machines and our refrigerators, and cars have just chips all over the place doing all sorts of things. So they are ubiquitous. And it's really this, there's electronics that we can see, there's electronics that we can't see, they're everywhere. Now, the computer is an electronic element, but it's big, it's not nano, okay? So when I talk about nanoelectronics, what I really mean is the fact that the big electronics are run by the little electronics. It's like, big fish, little fish sort of thing, right? So in this case, little fish is more important. If you crack open your computer, which you should only do very carefully, then you'll see the motherboard. This is what runs the computer, and then the most essential part of this is the microprocessor. That's where the processing is done. And the important elements in the microprocessor are the transistors. So when you think of a computer process, you think of bits, a 0 or a 1, and you encode information as bits. Numbers are encoded by, 3 bits can encode every number, or letters and things like this. So what defines the 0 and the 1? It turns out that's just the on and the off of a transistor. Whether a current is flowing through a transistor, that's a 1, and if it's not flowing, then that's a 0. So our bits are actually this basic element, right? And on the microprocessor, to do the processing that we do now, we need billions of transistors, now trillion transistors per chip to do the processing that we have. So as you can imagine, a lot of research, a lot of basic research focuses on improving just this one element, making it more effective, making it have less power, and making it smaller. Because at the end of the day, the size of the computers depend on the size of these. Yeah. Okay, so, just as an aside, sort of, the ubiquity of chips in everything that we interact with almost is actually a major factor in the current global supply chain problem. And probably everyone here has seen news stories about it's hard to buy cars. Everyone knows about the global supply chain? Okay, nodding hands, yeah. Okay, good. On the same page. Everyone start out on the same page. Okay, good. So there's, I read the Times. You'll see a lot of Times things, so that's my go-to. But okay, the tiny parts, big ripple, global chip shortage topples the auto industry. So what does this mean? How did that happen? It turns out that during the pandemic, people just weren't going anywhere, so there wasn't as much demand for cars. So the auto industry cut back on their need for chips. They just ordered less. They go into the cars. At the same time, we're all home Zooming, and so the computer industry backfilled that demand, and the people who made chips gave all of their orders to the computer companies and cut back on the cars. Now, when automakers resumed production, it turns out that chip suppliers had already given away their capacity, and there is no more capacity for automobiles. Okay? So it turns out that you can't get cars now because of the lack of chips. Chips that cost 50 cents, a quarter, $1, right? And the lack of these preventing entire production lines of cars. Okay, now you might say, well, okay, just make more chips, right? And make more chips fast. It turns out you can't make more chips fast, or can't even make them that easily, precisely because they're so small, okay? Or, chips are small, transistors are small, right? So because transistors go on chips, and transistors are now 20 billionths of a meter in diameter, they're really complicated, right? It's hard to make them, it's hard to pack them in. This is really, really specialized. It's difficult, it's expensive, and in fact, it costs over $20 billion to make a single chip factory, right? And 2 to 3 years to build it. So that gives you a sense of scale. Right? It's really, really hard to make these effectively. And in fact, because it's so expensive to make these chip factories, especially for every for new, smaller chips, you have to keep changing it and keep modifying it. And so by attrition, most companies just didn't want to put up that cost. And so it turns out that most of the chips are made by just a few companies. And in fact, one company, the Taiwan Semiconductor Manufacturing Company, or TSMC, dominates all of the advanced chip making. Okay, so if you look here, this is the entire market for chips divided by the size of transistors. Okay, and so you can see this dark blue is TSMC, and one of the things you might note is that TSMC has 90% of the market in the smallest transistors, just one company. So when TSMC has production issues, which it is now, everyone's hit. There's nowhere else to go. And I also want to mention, just for people who care about politics, which we all should a little bit, maybe a lot, I don't know, none of these companies are in the US. And all of our chips are in Taiwan, geopolitical issues, stuff, right? So, not getting too much into it, but this is something that in physics we've been talking about for a while. But when the supply chain problems happened, and the U.S. government suddenly realized that they were hobbled by the production of a single company in Taiwan, they were scared. They realized that this is a really big issue here. So the response was yikes, and also the Chips and Science Act. Okay, so this chip, they hurried through this new congressional legislation. This just passed in this past July 2022, and this act gives $50 billion to help domestic chip production facilities, as well as money for chip research at universities, and money to increase the chip workforce. And so I read something that we need like 90,000 new workers in the semiconductor industry who know about transistors and stuff. So if any of you guys are interested in physics, right, and engineering, right, then we need you out there. Okay, so this was a little tangential, but it's also telling you how important and integrated chips are into our lives, and how the transistor, this really basic element, is setting the scale for all of these sort of geopolitical shenanigans, right? Just understanding the transistor itself. So now I'm going to move on to the more sciencey part, which is saying, let's get to the science of transistors. What are we? Okay, this is another aside, but I feel like we're affected by all these things, by all these scientific and technological things, and it's actually really important for us to understand them at some level. Like, why do they happen? Where are the limitations? How do we overcome them? And even just understanding, what are transistors? How do we study them? How do we make them? Can they keep getting smaller? What happens if they don't? And what's next? Okay, so that's where we're going now. And we're going to start with basic electronic devices, because transistors are electronic devices. I started out talking about just basic electronic devices, but what do I really mean when I talk about studying electronics? I don't mean like, looking at the top of my computer and seeing how pretty it is. I mean studying the behavior of electrons. Okay, so when we study electronics, we study how electrons flow through material. Okay, so materials like metals have atoms in them. The atoms have a nuclei and electron. And in a metal, the electrons can move freely. Okay, so you have this kind of bath of electrons flowing through metals. And if you put a voltage across it from battery, the electrons will move from one side to the other. And we study how that happens. That's the study of electronics. So, here's my little schematic, not mine. Someone's schematic. There's a battery, there's a lamp, and you get electrons flowing out of the battery, and they light a light bulb. And that's your circuit. That's an electronic circuit. Okay. Now, when we do experiments on these, what we really want to understand is how well the materials conduct electrons, and what's their resistance to electrons flow. How bad, if they're poor conductors of electrons and they have high resistance, for example. And probably some of you have done this before using a fluke. That, I don't know, I use mine at home just to check whether batteries are still good. Anyone use a fluke? Yes, everyone. To check the batteries are good? Yeah, that's what we all do. Okay, right. So, but when you're checking across a material, this is what a resistor symbol looks like, and so we use a fluke to measure a resistor and to determine its properties. Okay, we use very fancy flukes in our lab, but basically that's what the circuits boil down to. And we sometimes will represent circuits like this, where this voltage is our battery, and then this is our wire, and this is the material of interest. Now, for most materials, like metals at room temperature, there's a very simple relationship between the resistance and the voltage you apply. That the resistance is just equal to the voltage divided by the current. That's Ohm's law, and that works a lot of the time. And probably people who have taken first year physics remember that, if not anything else. Right? V equals IR. So Ohm's law is fine. It's not super interesting from a physics perspective. So what do we care about from a physics perspective? What we care about is cases where Ohm's law doesn't work. I see laughter over there. Is Ohm's law interesting? I don't know.
Yeah.
There's other physicists, I don't know. They can weigh in during the question period. I didn't think it was controversial yet. Geez. Okay, so moving on. So from a research point of view, what we really care about is looking at new sorts of materials and understanding how they change their conductance or resistance. And so as an example, right, I can start with a simple circuit like this. And let's say I just add molecules to the resistor. Okay, I have a way that I can just add molecules to that material. And if the resistance changes when I add those molecules, that's a sensor. Okay, so that's, if the resistance changes, I can measure how many molecules I added, maybe measure the type of molecules. That becomes an interesting electronic device that I can study and utilize. Okay. Or if I take this, again, simple circuit, and let's say I add a gate that changes the energy of that resistor somehow. And let's say that if I apply that gate voltage, the resistance goes to infinity, so no current passes. That becomes a transistor, like a switch, right? I've turned it on and off with a gate. And so now this is another interesting electronic device that I can study more and use. And that's what we do when we study electronics. And I'll say more about that. Okay, so that's electronics. Why nano? Well, obviously everything's getting smaller, right? We want smaller sensors, smaller computers. We want little small robot drugs that can course through our veins and deliver, drugs where we need it. We don't want small spy robots, but we're probably going to get them anyway. In general, we want smaller things. So I'm going to go right to the example now of computers and how we got to the small computers that we have, again, going through transistors. But to go through the history of computers, I want to start with the first computer. This is a mechanical computer. This is the Babbage machine from 1832. I actually thought this was really cool because I actually had no idea how it worked, and so I still kind of don't. I keep having to look it up on Wikipedia, it's really confusing. But it's interlocking gears, right? And so it's kind of like a watch, right? The same way the watch changes the numbers on not a digital watch, but you know what I mean. Okay. Traditional watch uses gears to change the numbers. What this does is it keeps registry of different types of interlocking gears. So when you pull a lever, it connects different gears, and so if you have like 1 + 1, it'll actually connect it via some lever, and then some register at the bottom will come out with 2. Okay, so if you want to do advanced calculations, you have to pull the lever like hundreds of times. Okay, but it was mechanical, right? And you have to start from somewhere. So we started from here. It was 5 tons and 11 feet long, but it was a start, 1832. It's actually really, if you think of someone doing this in 1832, that's pretty impressive, right? That most of us couldn't do this today. Okay, but from there we moved on to digital electronic computers. The first electronic computer, 1946, the ENIAC. This used electronic charges rather than these mechanical registers to store numbers. And you can kind of think of this like an abacus. Okay, I know no one uses abacuses, but you can picture one, right? Picture little beads that register like the hundreds and the tens and the ones and stuff like that. And every time you move a bead up, you store information in that position of the bead. Now imagine instead of storing information in the position of a bead, you store it in a current, like a 1, right? Where a charge is. So if the charge is there, then it's like the bead being there. If the charge isn't there, then it's a 0. The bead isn't there. Okay, so that's how this digital electronic charges can store information rather than mechanical registers. So this used currents. It actually used vacuum tubes. And I'm old enough to have used these old style, the big TVs when I was younger. I see the 2 front rows on the internet. But in the back of the TV, there was an electron tube, and it was just a vacuum, and it had a cathode and anode, so you could put a voltage across it, and then the charge would go from, electrons would go from one end to the other, and they'd raster across a phosphor screen, and that's how you got your image. But it was really big, right? Because you said these vacuum tubes that you could turn on and off to get electron flow had to be pretty big. And that's what they used here as their on-off bits, these on and off of these vacuum tubes. And so even though the vacuum tubes were eventually made smaller, by smaller they were like, they started out, several feet, and they ended up at like 6 inches, right? So every bit was a 6-inch piece, okay? And so as you can imagine, this thing, took up a room, right? And it only had could perform 5,000 operations, which is not very much compared to today, and it crashed every 2 days, which isn't so different from it was when I was a kid. But It still, it still was the electronic computer. But it had these vacuum tubes, and you couldn't really make them smaller because they weren't, you just couldn't make tiny versions of these. So how did we get to where we are today? We got there through John Bardeen. And I have a soft spot for John Bardeen. Not only was he an Illinois professor, which I have a soft spot for, he was also a super nice guy, apparently. And so everyone in the department realized, like, no one could be a jerk because John Bardeen was so nice. And if the nicest person has won 2 Nobel Prizes, then, so he did. So he's the only person to win 2 Nobel Prizes in the same field. He won 2 just in physics. And one was for inventing the transistor with a team of 2 others. And the other was for the theory of superconductivity, which seems like this esoteric thing. Actually, Leon Cooper was one with him, who was his student, who was a professor at Brown. But what I love is that John Bardeen just thought really seriously about how materials worked, and so it allowed him to just think so broadly in totally areas that to us seemed really different, but to him was just connected to nature. Okay, so what did Bardeen do? This is the first transistor, it's pretty big. What Bardeen realized is that you could make a material that you could switch on and off with a small voltage and get a big current out of it. But it was a solid state material. And the importance of having a solid state material, you know what I mean by a solid state, like a thing. like a piece of thing, right? And the difference between a piece of thing and a vacuum tube is that your piece of thing can be made really small, right? You can scale it. You just have to do better engineering to scale it. But the physics properties are there, and then it's just engineering that allows you, it's hard engineering, but you can do it. It's possible to do, to scale solid materials in a way that you can't scale vacuum tubes and other things. So the idea behind this is basically this. It's material that had, let's say, electrons on either side of a region that didn't have electrons, that had a lack of electrons. But then if you applied a very small voltage to this region and added just a couple electrons, suddenly a huge current would flow from end to end. And so what that did is that you can take a really small current to switch on much larger currents. And so it's very efficient and also very powerful and a very good switch. And so then you can just do logic with this. A current flowing is an on, you just apply a voltage, that's an on, that's a 1, and an off is 0. And so this was the first transistor. You can see it was pretty big, but since then these things have scaled down tremendously. So if you look a little bit more closely at your microprocessor, what you see is a circuit that looks like this. This always reminds me of the way that cornfields look in Urbana from the sky, but it's not. It's an integrated circuit. This was the topic of another Nobel Prize, and deservedly so. And then you look at the region where the transistors are, and you see something like this, which reminds me of spaceships. I just think of other things. Okay, but what you're actually seeing here is a cross-section of a chip, and these things here are the metal interconnects that get down to the transistors. If you're wondering how you can put 1 trillion things on a circuit and still connect to them, you need to use that third dimension to get down and address everything individually. And they do this by layering on different metals that give you those pathways. And so these are the metal pathways. The transistors are these things at the bottom. If you zoom in on them, they look like this. And it's kind of like that diagram I showed. There's a gate on top, and then the current has to flow from either side. You apply a voltage to the gate, and the current flows. But as you can see, the modern transistor, unlike the thing on the previous page, is now nanometers, billions of a meter in size, compared to these things that were hand-sized. Okay, so Gordon Moore, who was a co-founder of Intel and its former CEO, what Gordon Moore did is he founded Intel around here, and he saw 3 points along a line and decided that would continue forever. And came up with Moore's Law. And Moore's Law said that the size of transistors halves every 18 months. Now the crazy thing is that, I don't know if it's Gordon Moore or if it's wishful thinking, but ever since he said that, people have just been working like crazy to make sure that as long as we can do it, the size of transistors halves every 18 months. It's like if we ever veered from Moore's Law, everything's going to be lost somehow. So, miracles of engineering. Transistors, which went from this thing, this used to be in the lobby of Bell Labs, it's this big, to this thing. And to give you a sense of scale, this is a human hair, 60 millionths of a meter. Here's a coronavirus. This proves this in a recent talk. This here, 80 nanometers, 80 billionths of a meter. And then here's a gate on a transistor. It's 8 nanometers, right? It's 10 times smaller than a coronavirus. So these are really, really tiny. And because they're so tiny, it means that we can pack more and more of these on a chip. And I should mention that the reason you want chips to be small and these things to be packed in is that your processing speed depends on how close all your transistors are together, right? So you might say, why not make one that's a meter big with like 50 trillion, right? Because you want them to be packed closely for faster processing. So that's why they have to be smaller on the same size chip. And this line has just basically continued until now. So in 2020, IBM has 7 nanometer transistors with 2.6 trillion transistors per chip. Okay. And that should be an impressive number because imagine, I don't know, even keeping track of a trillion things, right? But they do. It's really incredible what the semiconductor industry has managed to accomplish. Okay, so there's a problem here, right? You can say, well, why not? Why can't they just keep shrinking them to like a half nanometer or a tenth of a nanometer, right? Why not just continue on Moore's law? The reason we can't is because of physics, right? Quantum physics is causing us to reach the limit of where we can shrink transistors, okay? Quantum mechanics basically prevents transistors from being turned off when they're too small. And you can think of it this way. So you can imagine this is kind of how, this is another model of a transistor, electrons flow here, we put a gate on the middle, and we turn it off. And we expect that it can be turned on and off with a voltage. But now you can say, well, what if this region in between is so narrow that electrons can just go through it, even when it's supposed to be in the off state? Right? Imagine an electron being kind of long and extending on either side of this supposed barrier. Now that statement should be weird to you, because electrons aren't long, they're particles, right? But here's another trick of quantum mechanics. Electrons are particles, but they're also waves, okay? And waves do extend across space, right? They have a probability of being in many, extended across space. And this is something that Rosalyn discovered in 1924, that all matter has a wave-like nature. Okay, so we also, as matter, have wave-like natures. It turns out our waves are like 10 to the 10 times smaller than the universe is large. So we're not going to be like going through barriers anytime soon. Okay. I don't know though. Did anyone see Ant-Man, the original one, the quantum one? Remember the superposition woman, and she was kind of quantum-like, and that was cool. Okay, but not going to happen. And that's because the wavelength is inversely related to the mass. And okay, this is a bad equation because I didn't bother putting units in there, but they're like kilograms of meters. They're fine units. We're massive, and so our wavelength is really small. There's this 10 to the minus 34 thing up here. But electrons are not so massive. So when you have really light particles, their wavelength can be really big. And it turns out electron wavelengths are large compared to the size of barriers in transistors these days. And in fact, the fact that electrons are waves, you can do like interference with electrons, right? You can really prove experimentally that they're waves. And in general, now it means that if we turn off a transistor, then an electron wave can continue through the other side of the transistor with a thin enough barrier. And that's a property of waves that's a property called quantum mechanical tunneling. Again, it happens because electrons have this wave-like property. Okay, so now you can see the problem, right? If we have a thin enough barrier, then no matter what you do, you might think it's still a barrier, you've turned it off, but electrons are still going through, so you're not really turning it off, right? You're still getting a current through there, even though you think you've turned it off. And that's a problem. That happens usually for barriers less than about 5 nanometers. That's where we are right now with gates on transistors. And the industry is smart, they're doing all sorts of things, but basically, because of quantum tunneling, we get a current flowing without a voltage, right? We can't turn it off at low power because it's so thin. And if you try to run it at high enough power that it really makes a bigger barrier that nothing can go through, it turns out that if you did this for all of the transistors, that you'd get your laptop heated to something like the temperature of the sun, right? Which would really burn your lap. Okay, so that would be bad. So, we're at an impasse here. And actually, this has been noticed. Here's another Times article. I love the Times. Okay, so this is just from February of this year, and this is an article saying that Google teams were starting to report errors in their calculations that they couldn't figure out until they realized that it was because of transistor errors, with transistors reaching near physical limits. Okay? And this was a kind of hidden article in there. It's like someone found out, but no one wants to talk about it. Right? So we are actually at the place now where we're reaching the physical limits of where we could be with transistors. So let's try to do a couple more. Okay, so what are the current ideas to fix the problem? Well, like I said, the semiconductor industry is incredibly good, right? They've figured out all sorts of ways of overcoming this problem so far. They strain the transistors, they use different sorts of gate materials, they put the gates around in different configurations. Now they're at like 3D gate architectures. They wrap the whole transistor in a gate to make it even more robust. And so, so far we're getting to regions where I never thought we'd go with transistors, down to 7 nanometers. Okay? But at some point there is going to be a limit. Okay? Where we are going to reach this limit. There's no known solutions as we go much smaller. And this is where research comes in. Okay? This is where we start looking at what are the new nanomaterials that we can use for the next generation transistors. Or just what are the new nanomaterials that give us interesting electronic devices beyond the transistor. Okay? So, and I say beyond the transistor because even if we never replace the transistor, you might say, okay, no one's going to make new $20 billion factories for other materials, but we will still have specialized cases where we need things that are just ultra small or much lower power, or that have a higher sensitivity to gate voltage, or have novel effects. And that's where we bring in new materials to study their electronic properties and see if we can induce some of these novel things with better power conditions, right? With less energy dissipated. And some of the things I'll talk about now are basically, well, just graphene. I'm going to talk about one material. But I mentioned other materials because I hope that you see that the thing I'll talk about today is this one particular material, but it does apply to a lot of different types of materials. I'm just going to talk about one, but there's a lot of research on replacements or supplements to the silicon industry. Let me get my timing is. When am I done?
Whenever you
No, seriously, am I supposed to be done now? No. Oh, good, okay. I really have a lot of this talk left. Okay, so, no, it's not too long, don't worry. It'll be fine, it's fun. Because now we're getting to the more physicsy part. Okay, so here's a new material. It's called graphene. Who's heard of graphene before? Oh, good, okay, this is so easy. Graphene is a single atomic layer of carbon. If you'd asked someone probably 20 years ago whether a single layer of atoms could be stable out in air, they would have said no. They would have said, oh, the atoms will evaporate or the thing will crumple up on itself. It will never be stable. It turns out that's just not the case. Graphene is interlocking carbon atoms, and not only is it stable out in air, but it can be produced in almost the simplest way possible using Scotch tape. So if you imagine pencil graphite, and you zoom in on it, it's these overlapping shards. That's what makes pencils so smooth, because the graphite sheets off. Then you can just take Scotch tape and just start peeling it off. You peel it off, you peel it off here, and you peel off the tape itself, and you keep peeling off the tape, and then you take your final 10th tape sequence and press it onto a substrate, and you get stuff that looks like this. These are the shards of this separated out. And then there's like little invisible regions on there. And if you zoom in, you can see shadows like this, and that's a single sheet of graphene. Okay? And that's under an optical microscope, which is incredible, right? So it's stable in air. You can see it on the substrate. You never thought that just a trick of interference you could even see it. And since you can see it and it's stable, you can measure it and manipulate it. And people just didn't even think of this. This was also the subject of a Nobel Prize, and probably the cheapest one ever, because tape. Right? Okay, so here we go. 2010, Gaiman both led about the prize. I love this quote about graphene because they talk about how it's amazing. It's the thinnest known material, the strongest ever measured. It's like a Superman. It has giant mobility, zero mass. It doesn't scatter. Has high currents. Blah 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 blah. Okay, it's a really really cool material because it is a purely two-dimensional material with that hexagonal structure of carbon. It turns out to have really unusual properties. And that's what the sort of thing I said at the beginning. You want to study these new types of conductance properties. This is a great material to do it. It's new. A lot of things are unknown. What does it do? Okay, okay, this is the only physicsy plot. The energy is given by two surfaces on top of each other. The only thing to point out here is that we live in a low energy world around zero, and the behavior of the electrons around zero is defined by this little point here. And what this means in terms of conductivity is that if we change the energy of the graphene with, say, a capacitily coupled gate, you get this V shape out of it. And I'll show later why this is important. I also want to mention that this graph itself was described, this energetics of the electron energetics of graphene. It was described in 1946 by this guy Wallace just as an exercise. Graphene didn't exist. He just thought it would be a fun and interesting thing to do. And basically it had no references for the next 70 years. and then graphene was discovered, and now it's like one of the most referenced papers out there. So you never know what your work is going to amount to and what time scale. So graphene carriers have high mobility, low density. They're gate tunable. They're really interesting for all sorts of applications, from sensors to solar cells, and also with a lot of basic physics. Okay, so even a simple graphene device turns out to be interesting. This is one of these tricks in physics that when there's a new material, the first thing we do is just put electrodes on it, cool it down to low temperatures, and just see what happens. Okay? So this is literally the device. This is the device that we made. There's a sheet of graphene underneath, and these are 2 electrodes that we put on there, and they just measure conductance across it. There's a schematic of what that looks like. There's usually a gate behind it. And even for this really simple, basic graphene device, you can get this super high frequency transistor. And so IBM showed this some years ago, that they can get something that has very little power dissipation and has very high frequency. So this could be useful for special applications, like in cell phones or radar or in the internet, where you want higher frequencies than you may want your computer, for example. There's vertical transistors that are made out of graphene that are really interesting. The only thing I want to note is that graphene is nanoscale in the vertical direction, right? It's 1 atom thick, so it's about as thin as you can get in this way, but it also does extend that way. So, it really is best you just utilize a nano-electronics that requires some layering or requires some sort of unique capabilities that graphene has. And in general, we do need to work on creating large-scale defect-free graphene before we can really implement some of these on a commercial scale. Okay? But the other thing that's really great about graphene is that it's very thin. Okay? So most electronic materials are hard. Okay? So like if you take a piece of metal, right? Okay, I was going to say spoon, but spoons are flexible. You take a metal plate that's thick, right? And you try to bend it, it's really hard. But if you take a piece of tin foil and you try to bend it, it's really easy. So how do you make things flexible? You make them flexible by making them thin. Graphene is already really thin, and it already has great electronic properties. And so it's a great candidate for small, flexible electronics. Now, why do we want small, flexible electronics? Well, because they interface better with us, right? We're not small, but we're flexible, right? Our components are relatively small and flexible. Our innards are small and flexible. So if we can find electronics that can non-intrusively interface with our bending bodies, then we're open to all sorts of new capabilities, okay? And so this is one of the great uses of graphene is as a flexible electronic material. Okay, there's an example. Do you guys remember when they made this flexible phone and they gave it to critics and then it all broke? Okay. It turned out it had a covering on it, and everyone peeled it off. They didn't realize they weren't supposed to, then they bent and it just cracked. So, we'll get there. But, I'm personally more excited about, flexible, electronic band-aids and things like that. Okay, so now I'm going to take one step back to be even more fundamental. Okay, we care about electronics, we care about flexible materials, we care about flexible graphene. But again, I'm a physicist. Before we start implementing flexible graphene devices, I want to know, how do electronics change? What happens when you bend something like this? Does it act just like it did before? Or do you get something different? Is the behavior new? Okay, this is really interesting from a basic physics perspective, because maybe we can induce new behaviors, but it's also interesting from an application perspective, because maybe you can induce new behaviors. Okay? So, it turns out that if you do apply strain to graphene, you get really interesting things. There's interesting things predicted. So this is one of the papers on this. It turns out that you can introduce energy gaps, meaning that instead of getting that V shape in the conductance, you get something that goes to 0, right? It can turn on and off like a transistor does, for example. Or it has large quasi-magnetic fields, new types of flexible devices. And here's an example of what happens when you bend graphene. This was an experiment that a colleague of mine at Berkeley did, where he actually was studying something else. He had platinum, and he put graphene on top of it. And then he had a very local probe that could look really closely at what was happening with the electrons on that graphene. And it turned out the platinum had these little nanoscale bubbles in them that was like 2 nanometers high. Looks like this. And when he measured the electrons around these nanoscale bubbles, they were all going in really tight circles. Okay? So from electromagnetism, we know that the thing that causes electrons to go in circles is a magnetic field. Like you put a field on, and the electrons have a Lorentz force that makes them go around. So tight circles mean strong magnetic field. But it turns out those circles were so tight that it would have to be a 300 Tesla magnetic field to produce circles like that. Okay, so 300 Tesla. It's really, really, really big. So the largest magnet you can make in the National and the High Magnetic Field Lab is, the permanent magnet is like 35 Tesla, and that's a huge wrapped wire superconducting magnet. If you go to 100 Tesla, the magnet will blow up because you put so much current through the wires that it becomes unstable, and then it heats up enough that the whole thing explodes. Okay, so at 100 Tesla, actual magnets will basically blow up. And yet, with a strain, this strained graphene on this small scale, you effectively have fields larger than 300 Tesla. Okay? That's amazing. You can start doing things now that you couldn't do before, just because of this trick of bending this material and changing its electronics. So this motivated us. This was done with a local probe, but we thought, okay, we want to do this in devices. So how do we actually see these sort of pseudo fields and these energy gaps on the device scale, right? On something that we can actually connect to and maybe use for something. So, our goal was to induce this device-scale global pseudomagnetic fields, which required us to really fine-tune the local applied strain in the graphene. And so you might think, okay, why don't you just stretch the graphene? Actually, I have a slide where we tried to do that, and it actually just ripped. And so, okay, we wrote a paper on that anyway, but that's not what we wanted. Okay, so stretching the graphene in that way is not so great. It turns out you need strain that goes in 3 directions like that, and aside from having like little stick guys pull on it in 3 directions, that's really hard to get just without doing anything else. And so what we discovered is that if we actually made periodic structures, like those little nanoscale pyramids across the device, then maybe we could get average pseudofields and average behavior that change the properties of graphene. And so that's what we did. We made we got local strain via these micro-pattern substrate features, and the graphene was pinned on top to get the strain array across the material. So here's an example of what it looked like. This is actually I had an undergraduate do this. This was the first time we tried it. He actually used something called a nano-indenter, and he just took a piece of plastic and then pulled the lever 25 times, which is really slow, right? And then cast a polymer in that and pulled it out, and he had these little nanoscale pyramids that we then transferred graphene on top of, which you can see here. And what we found, we changed the spacing of these pyramids, and what we found is that when the pyramids were pretty widely spaced, this is graphene on top of the pyramids. And you don't really see anything when the pyramids are widely spaced, but when they're more closely spaced, you see these bubbles that tells you the graphene was so strained it started peeling off the surface, right? It's like trying to keep something down with strain, it peeled off. And so this peeling off told us that as we could change the pyramid spacing, we changed the global strain in the graphene. Okay? So this is a great sign. It told us that this indeed is a way to control strain on the device scale. Okay, so now we want to do more with this. So we next moved to making these using nanofabrication. To give you an example of what we did, this is a silicon, I should have labeled it. Listen, this is a silicon oxide substrate. We put little copper masks on it, and then etched away everything that wasn't under the copper. And then we dipped it in another etchant and sharpened those up, put contacts on it, transferred graphene onto it. So in this case, you could either press tape onto it, or there's other ways of getting graphene from solution. Press it onto these little structures, etch the graphene away to make shapes that we could measure, and we ended up with graphene that we could measure those on top of these pyramids. Okay, and this is what it looked like. These are here's C, these are the squares. These are the sharpened squares, it's D. You can see the top of these is 20 nanometers, so they're pretty sharp. This is the graphene suspended on it. It didn't always have holes, so this is the area that had holes. You can see this is the substrate below, and this is the graphene pinned to the top of these things, and here's what the whole device looked like. So this is the graphene device that we're going to measure, and then these are leads that we apply current to and measure voltage across.
What's the vertical axis? How high are these things?
Oh, here, this is the same. So they're 100 nanometers or something. How high? They're maybe 200 nanometers high? Yeah. Okay, and so one thing you might want to know, you didn't know you wanted to know this, but you want to know, how do we know that they're strained, right? I told you that they pop up, but in this case, we didn't want them to like stick and pop up. We just want them strained and suspended and uniform the whole time. And so to do this, we use what's called Raman spectroscopy. This is a spectroscopy that measures the vibrational modes. And you can imagine that as you strain it, these vibrational modes shift. And it's actually known that they shift along a certain line. So vibrational modes will shift along what we call this strain line in a strained material. And you can see here, this is our original flat graphene, and this is our patterned graphene, and it shifted along the strain line. And so we can see clearly that in a global, this averages over lots of these pyramids, so globally we're straining the graphene, and then when we measure conductance, this is conductance where red is a low conductance and blue is high conductance, that we're actually confining the graphene in certain regions because of these pyramids and the strain that we created. Okay, so now we can track electrons just because of this strain. Okay, so that's good, and it was interesting, but those pyramids were a little too far spaced apart for us. And so what we really wanted with a much higher strain on a more closely packed array to get the biggest effect. And so we next moved to these nanoparticles. This may not, you may think, okay, there's not a lot of strain, they're just nanoparticles, but these are all 20 nanometers in diameter. So you can think of these as just like an array of those tips that I showed, those tiny little tips. Now we took all of those and packed them close together to get the highest strain that was possible here. So here's a picture of the nanoparticles. They kind of create their own little crystal, and then we put the graphene on top of them. This is just a simulation of what the graphene looks like on top. It's pinned at the top and kind of relaxes in between. And again, what we found is that this same picture of the Raman spectroscopy, if we start with the flat graphene, right, and then we move to graphene on 200 nanometer nanoparticles, it's strained. Then we reduce the size of the nanoparticles to 100 nanometers, it's more strained, 50 nanometers, it's more strained, and 20 nanometers, it's even more strained. And so now we have a really robust way of both understanding and controlling the global strain in graphene by putting it on these nanoparticles, which is very exciting for us. Okay, so now we want to do even more transport measurements on these things. Here we just, we contacted it, we put a gate, we changed the potential of it in the back. Here's an optical, or actually scanning electron microscope image of what this thing looked like. You can see the nanoparticles there, okay? When we measure this thing, we look at conductance as a function of this gate voltage. What you see is this black line is just flat graphene, and there's this central dip that's based on just electrons filling in the regular graphene lattice. Okay, so that's just these hexagons. So this regular graphene lattice gives you these dips, but then you see there's another feature here, and this other kink is where electrons fill in the superlattice formed by the nanoparticles. And so this is an example of creating energy gaps, so changing the electronics of it by creating this superlattice of nanoparticles, which disappears when the strain is relaxed. Okay? And the last thing I'm going to show you, just as I talked about, is we also could see the effects of pseudomagnetic fields. And okay, I can go into more detail on this plot if you want me to, but just believe me when I say that this is, again, this is low conductance, and blue is low conductance, red is high conductance. This central region is what you expect just for flat graphene, and then it mimics itself at finite energies for the strained graphene, just like you saw the energy gap before. But the really interesting thing here is that you see kind of features that change, and they change because what we're seeing is the interplay between external magnetic field and the pseudomagnetic field that's global across this thing. And so we worked with our theory collaborators who showed us that we had basically a 5 Tesla global pseudomagnetic field. And then we went back and measured it locally. You can see that we had at least 50 Tesla of a local field, which gave us a global 5 Tesla pseudo field. And so finally we're where we wanted. We can actually measure and use these pseudo fields on the device scale.
Organizers, I was going to ask, pseudo versus?
Right. So yeah. So like I said, if it was a real like when you, so a real magnetic field will affect the spins of electrons. So just there's a quantum mechanical property called spin, and the spins align when you have a magnetic field, and it actually is like, it's electromagnetic, right? These fields, and you have to have a magnet to apply it, or moving electrons, but it's an electromagnetic field. In this case, it's not a real electromagnetic field. What it is that because of the way that you're bending the graphene, it changes the possible paths that electrons can take. So now, instead of the electron feeling a force due to an electric field, it actually feels a force not a force, it actually is constrained to a path because of the way that the bent graphene is. So you can think of it as probability. It has very little probability of going out there, but more of going around the circle. And that's why we call it a pseudo-field. So it's not actually affecting the spins, but it is causing electrons to move in circles, which is different, right? Kind of cool. Okay. Okay, I feel like I'm going over time. I'm going to end. Okay, you can globally control strain and graphene. I just want to mention there's a whole zoo of 2D materials you can do this to. You can control it in all of those. There's lots of interesting applications like, making solar funnels on a global scale. This is something that my collaborators have been working on, looking at deformed graphene heterostructures as sensors. They actually have made a really nice COVID sensor that people are interested in commercializing by using this sort of bent graphene on this scale, and so we're working with them on this as well. And generally, there's just a whole world of things you can create with strain in 2D nanomaterials. So, there are some transistor applications and bandgap modifications, but there's also just a whole bunch of other things you can do once you start looking at this sort of interesting device physics. Okay, there's also cool stuff with other transistor materials. I'm just bringing it back to transistors here. You can ignore this slide. I'm not going to talk about quantum computers because I don't think we have time. Do you want me to?
We have until 7, so if you ran another 10 minutes, say.
Okay. Oh, I only need like 2 minutes.
Then do it.
Okay. I just feel like I've said so many topics today. I hate leaving out quantum computers because, everyone's talking about them. So, okay. So, and they're not really related, but I hate not saying it. Okay. So, but my point is that, I talked about novel types of devices. I talked about transistors. Again, I just want to be clear that, people are studying these with all sorts of different sorts of materials, with bent graphene, with moly disulfide, with germanium nanowires. There's a whole world of new opportunities, new materials, new types of electronic devices out there. And they're really exciting to study, and maybe some of them will even be useful. So, okay, I only have 2 slides on quantum computing. This is a little bit different from what I've talked about, but I just want to mention that we've talked about quantum mechanics in the context of transistors, of particles and waves. We've talked about how quantum mechanics prevents us from turning off transistors. But quantum mechanics can also be incredibly useful. And in particular, it can be useful in what we call quantum computers. Right? So quantum computers use qubits to perform more calculations. The basic idea here is just this. A classical computer has a 0 and 1, right? But a quantum computer uses the wave properties of electrons to get superposition, basically. Right? And when you have superposition, you can imagine having a wave that's, that's twice as big, that interferes with each other to be 0, that has different phases relative to the other. So when you have this opportunity to have different phases of the bits, out of just 2 particles, you can get many more states or many more bits. And that allows you to do many more calculations with a quantum computer that has these phase relationships than you do with a classical computer that just has particles. Okay? And so that's the idea behind these things. So to give you a sense, a classical computer would need 2 to the n calculations to operate on n bits, 64-bit computer. So for a 64-bit computer, a classical computer needs 2 to the 64 calculations. A quantum computer only needs 64 calculations. Okay, you can see how that scales, right? 2 to the 64 is 64. That's a really big number versus a really relatively small number. So that's the idea behind these. There's lots of different materials, electron spins, and other things that can be used as quantum computer qubits. Here's one that I loved as a postdoc that had a carbon nanotube with just different regions where you isolate electron spins and call them qubits. This is not the most popular quantum computer these days, but I'm just using as an example that we can use new materials, and quantum properties themselves are useful for the next generation of computing, even beyond any sort of classical transistor. Okay, with that, I'm going to end. We talked about nano-electronics, we talked about ultra-small transistors, we talked about supply chain problems, we also talked about limits to transistor sizes and quantum effects. Talked about new materials, flexible graphene devices, a tiny bit about quantum computers. And what I really hope that you'll walk away with is that we really are trying to push the frontiers of science and technology, hopefully with the ultimate goal of just improving our lives. So thank you very much for your attention, and I'll take any questions.
Everybody, as professor, we can yell and scream. But what we like is, instead of having mics in the aisle, there's mics going around. So if you have questions, raise your hand and somebody will give you a mic. So here is a mic. All right, here comes another one.
Yes.
Thank you very much for your wonderful talk. I'd like to ask you maybe a basic question. I'm not a physicist, so you're going to have to educate me. What's the connection between those smartphones a few years ago that were overheating and causing fires in your talk?
I think it was I believe it was the batteries in those overheats. I don't remember this. It's the batteries. I mean, so batteries are generally, batteries are chemicals that when they combine release charges, right? Release electrons. That's how they work because that's why you don't plug them into the wall all the time. And so in that case, if you don't control the chemical reaction of the batteries well enough, or especially if you try to draw a lot of power out of your phone, right, which draws a lot of power out of these chemical systems, and you don't control it, you can get a recombination of charges in the battery that will just cause it to heat up. So this is another way of saying nothing comes for free, right? If you're gonna release if you're gonna use things for order, like to push charges around, you get heat out the other end. Okay? And so the more that you try to pull power from these batteries, the more they end up heating up. And I think that they just got the balance wrong. That was my understanding of it. But in general, there is an issue with this heating of computers. And actually, it's important because anytime you put a current through a metal, you lose energy. And that energy is just lost to heat. Right? So every time your laptop heats up, that's heating in the transistors and the interconnects of your wires. And that's just lost energy. Right? And so when we talk about these server farms, right, they lose energy just because of this heating, right? That's why they have to be cooled. That's why they're incredibly inefficient. So if we can figure out better computing elements that don't lose energy in that way, that would be huge in terms of just saving energy and and being kind of saving our environment at the same time. So yeah.
Very good. So thank you very much for your introduction. I think it's really robust and really clear. I didn't have some of the background knowledge, so if I pronounce something not correctly, please remind me. So we noticed that you mentioned the ultra small electronics, especially the size of the transistor. The length of the gates becomes smaller. So we use another material that is graphene, right? And you showed the structure of the new type of the transistor that use graphene, but the overall structure doesn't change that much. So how does it really make the things feasible in a smaller size again?
Yeah. No, that's a great question. So I just kind of I said that it doesn't, and then I moved on really quickly.
Okay, sorry.
Yeah, no. So this is a really, really important point. So transistors made of graphene itself aren't smaller in this direction. They can be thin in this direction. And so for graphene specifically, it's not necessarily making it smaller on the lateral scale.
Mm-hmm.
It can be thinner than the other ones,
Mm-hmm.
but also it just has new properties. But you're right, if you want to make something that's actually smaller laterally, then you have to use a different sort of nanomaterial. Right? So you do very similar things to what I just talked about, but with a nanowire or a nanotube or something like that. Right? So graphene is thin, but not. Does that answer your question?
Yeah, and there are different structures of the transistors. There are things that the two N-type semiconductors are on the side, and on the bottom is the P-type, and there are also tunnels, things like that. So for those tunnel-shaped transistors, the I don't know, is that the SiO2 things? I don't know how to pronounce that. It's it's vertical, right?
Yes.
So if we replace that with graphene, can they do that? I mean, if they do that,
Like that.
yeah.
You could. You'd have to pattern it down to really small scales like that. But you probably wouldn't, because it's, so right now the transistors are going out like this, right? So graphene would probably still be, I guess you could put it on its side. And it's a nanotube. So you can do almost anything. The question is it going to be efficient? and my guess is that a graphene won't be super efficient compared to silicon in this context, right? Whereas something like a nanotube, right? There are things that you roll graphene into a really small 1 nanometer diameter tube. At this stage, I could imagine something like a single nanowire that's really narrow, coated with a gate, and then packed really close together, right? Those could be 1 nanometer in size, but pretty robust. That could be better than what silicon does these days. Does that make sense?
Yeah.
What's weird about it is, again, what you care about is just packing as many as you can next to each other, right? It can be tall, it just has to pack next to each other. So different types of nanomaterials could work with progress.
All right, thank you. Thank you very much.
Okay, so 1 and 2, behind you, and 3.
Thank you very much for the talk. I'm a simple engineer, so it's going to be probably a simple question.
I was joking about engineers.
No, it's okay. So I was curious about, would it be possible to actually wrinkle the graphene and then cause quantum tunneling, electron tunneling between 2 adjacent atoms? So like you crumple it just enough, and you have a very small gap,
Yeah.
and perhaps you could even have another sheet that would be the gate,
Yeah.
and create a tunneling effect. Does that make
No,
sense?
that's it. So
Does this exist?
No, it does. So what you described is the new great thing in 2D materials. It's not by crumpling it, but it's by layering them. And so what people, which I think is maybe what you're talking about. So what people do, and this is one of the great things about these thin materials, is they make stacks of them. And so you can use different materials where you can have like this guy, and then this thing could be an insulating layer. So it creates a tunnel barrier, and then another thing, and then maybe another insulating material, different sort of functional materials. So by layering them, including insulating barriers and conducting and maybe ferroelectrics and maybe magnetic things, you can create entirely new sorts of material properties by doing that. And I think maybe that's getting at what you're thinking of. Is that
Yeah.
you're intuiting like just the cutting edge of layered materials right now.
Good to know. Thank you very much.
So Stefan in the back there, and then, would you be so kind?
Professor Rose also counseled me to ask the crazy questions, so I was going to ask. 2 questions, and they're really outside the box, in the spirit of the thing. Okay, the first one is, it's very naive. Is there a superconducting story with graphene? Because I know you also think about that too.
That's the rest of my life I think about superconductors. Yes. So this goes back to the previous question. So superconductors are materials that have 0 electrical resistance, which is great. So I just talked about all the power being dissipated and all these things. The problem is that they only superconduct mostly at very low temperatures, which is not so great if you want. If you think it's hot with your laptop, it can be really cold. So whatever, outer space cold. So graphene by itself doesn't superconduct, but if you take, this is so great, if you take a sheet of graphene and then take another sheet of graphene and imagine them exactly the same on top of each other. Now you twist one with respect to the other at an angle of 1.17 degrees, it superconducts. Yeah.
I have you
We're
said,
gonna leave it at that. You can learn more. So it has to do with the fact. Remember I talked about this superlattice thing where I said you create a secondary lattice in this case. What happens is as you rotate one with respect to the other, you're basically creating a new material with a much bigger lattice because they interfere in such a way that you create these patterns on it. And so that bigger lattice has stronger electron interactions, and that causes superconductivity.
so it's like a Maury pattern, like one of these psychedelic things.
It is literally a Maury pattern.
Oh, awesome.
Yeah. That was the terminology.
And I have some biology colleagues in the audience. I was going to ask the question for them. Is there a biology story with graphene?
Is Bob hurt?
There's a biology story. There you go. See, that's an electrolyte cell with DNA, RNA, etc.
So much for me listening to your talk.
Biology. No, that's okay. I went over this quickly. So deformed graphene makes a really great sensor. So it turns out as you bend it, because the electrostatic properties change, molecules stick to it better. And actually, they don't stick to the dips because it's not like they're being trapped. They actually stick to the peaks because they become more charged. And so it becomes much more effective at attracting molecules and sensing them than just flat graphene or even any other material. And so, my colleagues are working on making a sensor out of this. We're trying to they just crumple it, but we try to make these regular arrays for them to test it on to really quantitatively do it better. So is that a good enough biology story?
That's a great job.
Oh, great. Good, I'm off the hook.
Just tap it and see if it works.
Well, thank you so much for this wonderful talk. And I just have a small question that when we talk about high conductivity, so we have graphene and then there is carbon nanotubes. And these days, there's a lot of going on M-scenes, right? It's a 2D material,
Like MC.
M-scene. So I just want to know.
Yeah, so they're not on here, but okay, something like that.
Okay, so I just want to know what's the future like nanomaterials that for the next 10 years, what could be the materials that can be used for high conductivity?
So I think for high conductivity, graphene's actually really good because it's relatively simple, right? I think that what we really want are materials that are functional now. So I think the next generation of materials are going to be the magnetic or the ferroelectric, right? Or thermally effective 2D materials. I think those are the ones that we're still discovering and trying to figure out the properties of. So I think functional 2D materials, either intrinsic or made by stacking, are going to continue to be probably the biggest thing for the next 10 years. And by stacking in different ways, because it turns out everything you do to it, you get a new material. It's like a playground. So I think that'll continue to be really interesting for another decade.
I think so. One and then two. If you could pass this mic back to this gentleman.
Yeah, just a quick question. So, what's the largest factor that prevents us from using these new materials today?
Yeah, that's a fantastic question, right? Because I feel like you always give talks and say like, oh, this is so great, and then you just don't see it anywhere commercially. So there's a couple factors. One is that you need to have really good control over the material growth process and make them clean and reproducible in order to use them in manufacturing. So it's one thing to just use Scotch tape or to grow graphene in the lab. It's another to have big sheets that roll out that are reproducibly, defect-free. And that's the stage where we are right now, that it's really hard to make these on a large scale that are reproducible, defect-free, that don't rip, that we can then use in manufacturing. And so that's one of the biggest things. So the silicon industry, they have, part of the cost of these great growth facilities where they make these crystals of silicon that are like perfect to 1 in a billion defects. They're perfect, right? But we don't have that with a lot of these nanomaterials. And it's really hard to get because they're made in labs using small facilities and scaling it up is expensive. And then that's the other side of it. If we really wanted to, we could probably make these materials at scale defect-free, but it would cost $1 billion. So right now, silicon's kind of working. So who wants to spend $1 billion making nice graphene if we're not sure we can use it yet? So I think until we really need the material, we're not going to spend the money to make it perfect on that scale. So I think those two are working against us.
So it's not the lack of research, but the lack of investment that prevents us.
Yeah, mostly. Yeah, and you have to have a really good reason. Like it has to be definitively better than what we have, right? Not a little bit better than silicon. It's a little better than silicon. They'll just figure out a way to make silicon a little better than that. It has to be a jump better, and that's also hard. So special applications, that sort of thing. But then again, who wants to spend $1 billion on a special application? So these are the challenges that we have.
Is it okay? It's on. Do you think that there is an element of transhumanism almost to the biological applications of graphene research, as in assimilating with technology almost and transcending natural human biology?
So,
well, I mean, because you're talking about the medical applications about like almost merging with graphene sheets and like, I believe there's something also that I had written down about like messenger graphene in your veins even too.
Yeah.
So I was just asking about like the assimilation of machines. I just thought it was interesting.
What you're talking about.
I was giggling, but that's okay because it's a good question still. Don't let people dissuade you by this is here. So what's interesting is like this was this slide that I put up about the next industrial revolution. I mean, this is what you mean. Cyber physical systems are maybe what you're calling transhumanism, which is integrating electronic devices into our world and possibly our bodies. right? That is, I know, but that is what people are thinking right now of, do you want chips implanted that are going to monitor your health all the time, right? That are gonna tell you if your blood sugar is high, that are gonna tell you, if you're doing something wrong with your body at that particular moment. So I don't think that it's graphene per se, which is going to enable this. I think that there are already chips out there that can do it, and that we have to want to have that happen, or there has to be a really good reason for that. But I think the technology for that, that's now. I think that technology is basically coming online, and it will be more and more online in the next 10 years, and it's up to you guys to think about what you want to do with that. That's my feeling.
So, quick organizer's prerogative, and then I'll go to you. Is Bob Hurt or one of his students here in engineering? So no. So
I got it.
So Bob Hurt, apparently mosquitoes hate graphene.
Oh, is that right? I didn't know that.
And apparently,
Interesting.
they're been developing barriers, cheap, single layer barriers to prevent mosquitoes from biting you using graphene. And I don't mean like writing on yourself with a pencil. So there's another biological thing.
Yeah, I mean, graphene it's inert because it's carbon, but you also have to worry about nanomaterials, right? I mean, that's why there was a recall of sunscreens, because sunscreens, the modern ones, have nanoparticles in them. And that's great at reflecting the sun, but they also get absorbed in your skin. So, we have to think about how we use our nanotechnology. It's for good. I mean, is it better to get skin cancer or to have particles in your body? I mean, I actually don't know. I go for the particles in my body, because I know skin cancer will kill me. But it's again, this is part of us educating ourselves about what our, how we're being affected by the things we use.
So it seems to me that nature gets away with making very wonderful things with things that are not so fine as nanometers, but it's like really good at making huge things like a brain. So I'm curious to know if you agree with that, and if you don't, then how do you understand the brain as an electronic machine? What is your view on, if you were to get a brain and understand it with electronics, how would you describe it?
Yeah, I would describe it. I mean, it's an electronic machine that's connected in a much more sophisticated way than our modern computers, with more sophisticated electronics, actually. Okay, so
could you expand on?
Yeah. So the brain, it's not just a mass. There are, that you have nerves that connect to your neurons that fire, right, and give you signals in your body about when you feel things, about, you store information in your brain depending on how the neurons are connected. So there's an idea behind modeling the human brain, and the idea is that when you fire your neurons, it's not an on-off switch like a transistor. It's actually a peak, and that peak gets reinforced. Your memory is like you get a higher and higher peak every time you go through that same path. And so people are trying to make electronic devices that have memory effects like that and mimic the human brain in that way, and are trying to connect it in a way that the human brain is connected, and are just trying to understand how the human brain is connected in order to mimic it better. So I do think that the brain at the end of the day is a physical system. It's actually a physical electronic and chemical system. It's just that we don't know enough about it yet. We don't have the tools to do what biology has done so well. And the scale of it is microns. It's small. It's not maybe nanometer scale, but it's some microns, hundreds of nanometers. It is small. It's just better still, which is good. I mean, you want something to be, aspirational. Our brains are aspirational. Our actions aren't always, but our brains are.
Yes. Hi. We are Mayor Biomedical Engineers, and we, as fellow women of color in STEM, we just wanted to ask you, how do you keep up with your cool questions? So it's like nothing to do with the physics. Just wanted to appreciate how amazing you are. So thank you for coming.
Thank you. Thank you very much.
Another question.
So just a follow-up question with the body does. I agree with that.
Sorry, I was kidding.
Yeah, I do agree with that. Yeah. So my question is like in the investment perspective, as you said, like we will not like commercialize such a expensive material, except for we have a strong need for that. And in terms of there are many properties of this new material, and we can use this to in the new structure of transistors. But we have some chiplet technologies right now, so I probably don't think that will be the first field that this material might land on. So like, in which area, like in which field, do you think there might be a strong need for the graphene, like really recently, like in?
Okay, so one might be, graphene is pretty thermally stable, and so it might be in making heat-resistant transistors. Okay, and where are we need these? Let's say hypersonics, right? Hypersonics are materials that are like, you want to move an object that's way beyond supersonic, right? You call it hypersonic, but very, very fast, it heats up. That's one of the biggest limitations of hypersonic transport. So if you could make electronics on there that are insensitive to heat, which graphene is much better at, then that might be one application. Is that?
Yeah, it's like I thought of that property as well. It's just there are some like third generation semiconductor things that can really work in really hot situations and things like that. So how is that different? Probably.
How's it different? I mean, it's so I don't know what materials you're talking about. It could have similar properties, but maybe again you want to. This is really case specific. Okay, so I can't answer this really ideally specifically in this case, but again they work better at higher frequencies and at higher energies, and so if there are applications that maybe need both, then that would be a case where you use these. But more than that, I have to look at the various materials and compare them.
Yeah. Okay. Thank you very much.
There's one more.
Hi, I'm a member of Dr. Toussaint's group. I believe you know him.
I do.
I think you came. But my question is, if one of these nanomaterials, whether it's graphene or something else, takes strides and makes a place for it in the marketplace, is that going to lead to the inside of a computer looking completely different? Are we talking overhauls of systems, or are we talking about just nanometer inside a chip? That's what looks different.
Yeah, it'll look the same is the answer, because the inside of I want this one. I want this one. The inside of your microprocessor is still gonna this is the integrated circuit, and the architecture doesn't necessarily have to change, right? What changes is like the microscopic part of it, nanoscopic part of it. So I think your physical computer won't necessarily look different. It'll just be, the chip won't even look different. It's just what's on the chip will probably look different.
Right. I was worried about more barriers than there already are for like if you had to do a complete overhaul.
Yeah, no, I don't think you will. On the other hand, I think that we do get a little lazy when it comes to, people work really hard at the technology scale here, but they start working less hard as you go up, right? So they work really hard to make make more powerful chips, but then they use this architecture that's pretty much the same, and then the programs just hog as many bits as they can, and no one's actually trying to make them efficient. So I do think that what's going to change in the next few generations is making all the other aspects more efficient, which we haven't had to do yet, and that's work. So who wants to work that hard? But we do. We have to. So you may see changes just because there should be. Things shouldn't, they shouldn't always look the same. If they're not changing, it means people aren't working that hard at it.
Thank you.
All right, and that concludes our first post-COVID, thinking out loud. So thank you so much.